In this module, we'll first discuss multiplicative thinking, specifically focusing on arrays. Then we will model the use of number or problem strings. Then we're going to think about how students develop proficiency with multiplication, and once again, how different situations press different models and strategies. One of the articles you're going to read later describes the differences between these stages within this progression of thinking. Let's get started with how to help students develop multiplicative thinking. In your article, you'll read about the difference between additive thinking and multiplicative thinking. As a reminder, the focus for this part is on developing the thinking as opposed to solving a multiplication problem. In order to be fluent with an operation, students need to be accurate, efficient, and flexible. Without those elements, students are left with just memorizing as their only fallback. The important thing to remember is that when we're trying to develop multiplicative thinking, we need to develop the flexibility in the student thinking. If we go straight to solving multiplication problems, that doesn't develop their thinking. Although the problem is conventionally written this way in many U.S. curricula, there are other curricula that list components in reverse order, and that is also the convention in some other countries. These are mathematically equivalent, and we would never want to mark a student incorrect for reversing these elements. As students develop their informal multiplicative thinking in K3, they start to use spatial structuring to move these groups of objects into an array. In our cookie example, there is a progression from seeing them as 15 separate cookies to seeing them connected linearly and maybe connected to a number line, to seeing them stacked to really show the 3 boxes of 5, and then seeing them in array. An array is when objects are structured into rectangles of rows and columns. One thing we've seen in grade 2, as students are starting to grapple with arrays, is some students were still counting haphazardly, whereas others saw the rows of 5 or columns of 3. At this point, teachers can emphasize those student strategies that are more focused on the rows and columns, especially the students who are using skip counting to their advantage. From a grades 4-9 perspective, this is a concept to look for in students who are struggling with multiplication facts. Are they able to spatially structure? To find the area of a rectangle, is the student still drawing and counting individual squares rather than thinking in terms of rows and columns, and seeing how that related to the base times height formula? Having this background gives teachers a place to go to with those struggling students, working with them on spatial structuring and seeing the array as rows and columns, not just a bunch of squares. So far, we've been talking about multiplication as repeating or adding equal groups. As students progress into upper elementary and middle school, we start to expand the notion of multiplication to include scaling, which can result in both larger and smaller quantities and works with non-whole numbers. In the standards, the idea of scaling is first introduced in 5th grade. For example, I can say the distance I walk to school is 3 times the distance Mike walks to school. If this bar represents Mike's walk, we can find the distance of my walk by stretching or scaling it to 3 times the length. But unlike thinking in equal size groups, we can use more complex numbers. For example, I could realize that my walk is actually 3.5 or 3.5 times the distance Mike walks to school. So here's the 3 times plus the extra half. Likewise, we can multiply by numbers smaller than 1, 2. The distance Michelle walks to school is 1/4 the distance Mike walks. We scale the original bar back to 1/4 its length to find Michelle's walk. In this next section, we'll think about how students progress from these multiplication problems within 100 to developing more formal strategies that will work with larger numbers. There are 2 problems we'll be looking at. Please take a minute to pause here and work through these 2 problems. They're in your pause and play document. Play around with a couple of different models and try to consider how the different contexts drive the strategies and models you use. Feel free to record a comment, jot down a note as you're figuring these things out. Plus, press play when you're ready to start again. The first problem naturally leads to an area model. An area model is just like an array, But rather than thinking of objects configured in rows and columns, the area model is a little more abstract, showing the actual area of the rectangle. Eventually, we hope that students no longer need all the lines, that they can just use what they know to efficiently break up the area into manageable parts, finding the area of each. This can be done by place value, as shown here. But it could also be broken apart in other ways. For example, we could have divided the left side into two sixes instead of 10 and 2, and done 6 times 20 plus 6 times 8, and then doubled the answer since there's two sixes. But decomposing both numbers by place value has the advantage of connecting to more formal symbolic methods. For example, we could use the distributive property by doing 20 plus 8 times 10 plus 2. This gives us 4 small multiplication problems: the 20 multiplied by the 10 and then by the 2, and then the 8 multiplied by the 10 and then by the 2. This connects directly back to the area model, as you can see. And then partial products is just a different way of organizing this. Working left to right, let's take a walk through how these models progress. Now, I want to just have a little caveat before we go on. Hit pause if you want to explore these models on your own. The area model on the left, it is not a box method. It is not a window method. You draw a box and you do this and you do this. And I want to put in a note of caution here. Many times we see children completing the box as a procedure. It's important that children understand that the box represents an area of units, like a grid in the top right corner. Rather than draw every line for every unit, we're starting to group the units. If we're considering algorithms based on place value, we should think about the traditional algorithm too. Take a moment to look to see whether you can find the 56 and the 280 in the partial products or the area model. What problems do those represent? So in our traditional algorithm, we start by going right to left and doing 2 times 8 equals 16. Write the 6 in the ones place and regroup the tens to the tens place. Then we do 2 times 20 to give us 40 and add this 10 to give us 50. But of course, when we actually do this, we drop the place value, saying 2 times 2 plus 1. But we're really doing 2 times 2 tens plus 1 additional 10. Then we write a 0 below the 56. Why? Because now we're multiplying by tens rather than ones. So 110 times 8 is 8 tens, or 80. Then the 110 times 2 tens is 200s, or 200. Relating to the area model or partial products, the 56 is really 2 times 28, and the 280 is the 10 times 28. We're not just breaking those pieces apart. But once again, the traditional algorithm was built for compactness. The point is, turn off your brain and follow the steps. There are times when that is actually really desirable, but it's unlikely to develop student understanding of place value of multi-digit multiplication. The algorithm is just a tool that can connect back to the more transparent but less compact models, such as partial products and area. The data plan problem will tend to push students towards what we call repeated addition strategies. Hopefully they aren't just adding 28 over and over again, but we do often see students kind of branch values together to figure out the problem. Rather than using this inefficient notation, we want to press students towards using a ratio table, which is far more efficient. But we don't want to shortcut this. We don't want to say, here, let me show you this, and then I'm going to push you into ratio tables. We want to push them by changing the numbers that force them to use more efficient thinking to desire a ratio table. In all of these models, students are using the strategy of keeping one number intact and then either adding it repeatedly, doubling, scaling by some larger number. Let's compare these two. Here the student is doing basically the same as we saw in the repeated addition. They know 1 month, double to 2 months, double to 4 months, double to 8 months. Then we can use these columns to figure out what 12 months would be combining the 4 and 8. So I'm looking at, let me grab my pen, at this table right here. So take a second and just make sense of what the student did. How is it similar? How is it different to the other students? What you hopefully notice was that this student is using place value to be much more efficient. First they double, which is the same, but then they figure out, let's see, we're looking at this middle one now. First they double right here, but then they figure out if I just jump to 10 months, I'll have 280. Knowing that all they need to do is multiply 28 by 10 as well. So bumping up the place value by getting $280. Now that they know the cost of 2 months and the cost of 10 months, they can just combine those to get the cost of 12 months, which is $336. Going back to the idea that we can multiply in any order, that multiplication is commutative, we could also have done this problem this way, shown on the bottom right, though we lose connection to the context of the problem. Asking students to connect between solution methods is a key part of explicitly attending to concepts. Take a moment to mentally answer these questions and think about what this line of questioning is hoping to emphasize. Press play when you're ready to continue. These questions might be trying to emphasize that we can decompose both numbers or just one of the numbers. Visually, this ratio table would be represented by keeping the side of the rectangle intact. Students might examine the benefits and limitations of each. Specifically, that might be easier to add when we decompose by place value, but an efficient ratio table might have fewer steps. Again, we would never throw all of this at a student at once. These are concepts that develop over 2nd through 5th grade, but there's value to making sure students have exposure to these two different types of models. They help us connect across domains because ratio tables in multiplication support the use of ratio tables later for solving proportional problems and eventually for developing understanding of functions. Likewise, the area model connects to geometry concepts and can help students understand ways to manipulate quadratic expressions in high school. We also want students to select the most appropriate model for the task at hand. There may be times with very large numbers or decimals where having a more efficient algorithm is far preferable to drawing out something like an area model. That said, I'm in a point in my life where I'm much faster with partial products than I am with the traditional algorithm for multiplication, mostly because I have trouble remembering all of the steps. Let's do a little practice with this. You aren't actually going to presenting your work for this, but practicing the models a few times will help you write your reflection prompt in post later. Choose any two of these and solve each of them in a couple of ways. Then go to the next slides and we'll debrief on each problem. Let's take a look how we break down 47 times 34. One way, let's look at the area model first, right there on the left. So in this area model, we split the 34 into 30 and 4, and we split the 47 into 47, or 40 and 7. Then we do 30 times 40 is 1200, 30 times 7 is 210. That whole column right there totals 1410. Then we can do 40 times 4, which is 160, and 4 times 7, which is 28. That whole column equals 188. We combine those and we get 1598. Now let's move to partial products. If we basically do the same thinking that we did in the area model, we just write down all of our place values right here in the middle. There's no reason that like in the traditional algorithm, we have to hold on to them all. And this makes it much more explicit. So if we do 4 times 7, well, I'm going to start the way they did. They did by place value here. So 30 times 40 equals 1200. And then they did 30 times 7 equals 210. 40 times 4 equals 160, and then 7 times 4 equals 28. Add those all up. It's the same thing as adding all of my boxes here. Now, let's look at a ratio table. If I have 147, I can double that. If I have two groups of 47, I get 94. Three groups of 47, and then four groups of 7. With those four, I can actually make 34. So three groups of 47 is 30. So it's 140 or 1410. And then to get my final answer, I just have to put these two together. I have three groups, or here on this one, I have four groups of 47, and on this one, I have 30 groups of 47. Did I lose you on that one? Take a second to figure it out. All right, so rather than break this down for you, take a look at each of these models and see if you can see the connections between them. Start with the area model, go to partial products, then go to the ratio table, and then go to the traditional algorithm. Press play when you're ready to continue. Now this one's a really fun one. I actually really like to do these with base 10 blocks because they're more challenging than we expect them to be. But if we start with the area model, I have two groups. 2 times 3 is 6. And this one, they still broke it up. So 8/10 of 3 is 2.4. And that's something we can model with base 10 blocks. And we're going to do that in the place value task in a later module. I think it's the next one. And then I could do two groups of a half, which gives me a whole. And then 8/10 of a half. Or we flip that around. I said 8/10 of a half. We can also say half of 8/10. Well, half of 8/10 is 4/10. Then I can add those all up. We do the same thing when it comes to partial products. And then this, take a look at the area, make sense of the ratio table. And this is, and then compare, sorry, I'm losing my train of thought here. And then compare to this problem where we times everything by 10, and then we have to divide out tens. This is that compensation strategy. We don't just move the decimal, okay? We're multiplying by 10 twice, and that means we have to divide by 10 twice. Early experiences with grouping, spatial structuring, and arrays prepare students for developing mathematical thinking. Different contexts tend to drive student strategies that connect to different models. All connect to the general problem type of groups times members or the number in the group. Students need to be efficient multiplication strategies, or students need efficient multiplication strategies on both decomposing numbers by place value, keeping one number intact and scaling up or down. Different contexts tend to drive student strategies that connect to different models. Students need efficient multiplication strategies based on both decomposing numbers by place value, keeping one number intact and scaling up or down. Welcome to part 2. In this presentation, we're going to continue our look into developing multiplicative thinking. In this section, we're going to look more deeply at how students develop multiplicative reasoning and how those understandings connect to other foundational mathematical topics. When children are starting out counting and adding, they generally see objects one at a time, even if they are kind of grouped together, but eventually they're able to unitize, which means that they see those 5 objects as a new set of 1. So early multiplicative thinking starts when children begin to see these blocks both as 3 groups of 5 ones and also just as 3 5s. This is why young children are often encouraged to group or sort objects or to fill in frames with objects. We can then explicitly look at flexible thinking with arrays, connecting to the symbolic notation. Take a moment in your notes to draw any vertical or horizontal line to decompose the array into two easier multiplication problems. Think about how you would express your work symbolically. Press play and then press pause and then hit play when you're ready to go. As students develop some basic facts to draw upon, they can start to use those to do more complex problems. In this case, some of you might have seen this problem, 9 times 6 as 9 times 3 twice. We can write that symbolically using parentheses, decomposing the 6 into two 3's. This is a visual of the distributive property of multiplication over addition. Others may have taken advantage of the 5 times 4 within the 9, adding together 6 times 5 and 6 times 4. Or perhaps the student knows 10 times 6 and then just takes away one of the 6's. Having the visual either on paper or mentally helps us understand what we need to add or subtract to get to the correct answer. There are a couple of big advantages of seeing multiplication this way. First, we're connecting to the concept of area. Within the standards, both area and initial ideas of multiplication are intentionally introduced simultaneously. We are also starting to generalize some properties of numbers, such as the distributive property. Eventually, for most students, most facts will be committed to memory, but we wanted to make sure students have a way to use what they know to get what they don't know, so you don't run into the situation I used to as a math tutor, where a student could tell you 9 times 5 is 45, but then asked for 9 times 6, and would say, I don't know that one. There are lots of places that arrays appear in the real world, from ice cubes, eggs, muffin tins, to windows in a building and solar panels. These real situations can provide such rich opportunities for students to further develop multiplicative thinking by decomposing the array into manageable parts. Let's look at an example of a problem here. This is the baker's problem, which comes from young mathematicians at work. Pause here for a moment and think about how you would determine the number of muffins. People use a wide variety of methods to do this. Some look at columns, counting 8 5s and then 8 4s for a total of 72. Others look at these two as 10 rows of 4 minus 1 row to give 36 muffins, and then double that. Some see each flat as 20, so you have 4 20s, 2 4s. There are lots and lots of ways to look at this, but the point is that we want students to look for efficient ways to determine the answer and to be able to understand other methods as well. All this work that we do in building multiplication flexibility and fluency with derived facts connects to other content as well. We already talked about its connection to area, but these ways of structuring numbers also relate to the distributive property of multiplication over addition. It is, in other words, when we break down this area represented by 6 times 9 into 6 times 5 plus 6 times 4, we are developing the idea that we can multiplicatively distribute that 6 to the sum of 5 and 4. With algebraic symbols, we typically represent the distributive property like this, where you see A is distributed to or is multiplied by both B and C. Early experiences with grouping, spatial structuring, and arrays prepare students for developing mathematical thinking. Different contexts tend to drive student strategies that connect to different models. All connect to the general problem type of groups times the number in the group equals the total. Students need efficient multiplication strategies based on both decomposing numbers by place value, keeping one number intact, and scaling up or down. Multiplication concepts directly connect to the ways we operate with algebraic expressions. This is an opportunity for coherence across the grade levels.